Good day, grade 10. How are you today? I hope you're fine, healthy, and safe. I am Teacher Xiao, your teacher for today in Mathematics 10. Today, you will learn about generating patterns and arithmetic sequence. Specifically, you will learn how to define and illustrate an arithmetic sequence and determine the end term of an arithmetic sequence. Have you ever thought how the signs from around the world are formed? Have you ever noticed what gives beauty to all the things we see around us? How are patterns formed? Were you not puzzled as to how these patterns are arranged? A lot of things are arranged with special patterns. Some of the special patterns can be established using your knowledge of sequences. And to know more about patterns, let us have an activity. First up, for example, we have banderitas. The color of the first flaglet of the banderitas is green, followed by blue, then red, then orange, then yellow, and again green, blue, red, orange, and yellow. Do the banderitas show a pattern? If your answer is yes, then you are correct. This shows a pattern because the arrangement of the colors of the flaglets repeat after yellow. Now, how about if we have bunches of coffee beans? On the first bunch, we have 4 coffee beans. On the second, we have 6 coffee beans. And on the third, there are 8 coffee beans. Does this show a pattern? If your answer is yes, then you are again correct. This shows a pattern because there is an increase of 2 in each batch of coffee beans. Now, can you still remember your childhood practice, which is the close and open palms? But this time around, we have a different manner of doing it. First, we have a closed palm. Then after, we have an open palm. After which, we have another closed palm, followed by 2 open palms, followed by another closed palm, followed by 3 open palms. Does this show a pattern? If your answer is yes, then you are again correct. The number of open palm increases by 1 after every closed palm. Now, let's have the last example. The set of stones. In the first set, there is 1 stone. On the second set, we have 2 stones. On the third, we have 3 stones. On the fourth, we have 4 stones. And on the fifth set, we have 5 stones. Now, does this show a pattern? If your answer is yes, then you are right. Because in each set, there is an increase of 1 stone. In the activity, we just have learned that patterns can be seen in shapes and in nature. The patterns generated in the pictures are examples of sequences. So what is a sequence? A sequence is a function whose domain is either the set whose elements are 1, 2, 3 up to n, where n is a natural number, or the set of positive integers. Every element in the sequence is called a term and denoted by a sub 1, a sub 2, a sub 3, a sub 4, and so on. From the definition, a sequence is said to be finite if its domain is a set of 1, 2, 3 up to n, and is said to be infinite if its domain is a set of positive integers. Now, let's have examples of sequences. 3, 9, 27, 81, and the other is 2, 4, 6, 8, and so on. The first sequence is an example of finite sequence, since there is a last term. Considering the first sequence, 3, 9, 27, 81, we can clearly identify the terms as follows. First term, which is denoted by a sub 1, and that is 3. Second term, denoted by a sub 2, which is 9. Third term, denoted by a sub 3, which is 27. And the fourth term, denoted by a sub 4, and that is 81. And a sub 4 is the last term of the sequence. The second sequence, which is 2, 4, 6, 8, and so on, is an infinite sequence, since there are 3 dots or ellipses at the end, which signifies continuity of the terms. How about if you are asked to find the terms of a sequence? How will you find the next terms in the sequence? Let us consider the function a sub n equals 2n plus 1. Again, a sub n equals 2n plus 1. This function a sub n is considered as the general term of the sequence. Now, let's find the first 5 terms of the sequence a sub n equals 2n plus 1. For the first term, where n equals 1, we substitute n by 1. Thus, we have a sub 1 equals 2 times 1 plus 1, which is also equal to 2 plus 1, and that's equal to 3. For n equals 2, a sub 2 equals 2 times 2 plus 1, which is equal to 4 plus 1, and that is equal to 5. Now, for n equals 3, a sub 3 therefore is 2 times 3 plus 1, which is equal to 6 plus 1, and that is equal to 7. Moving ahead, we have n equals 4. A sub 4 therefore is equal to 2 times 4 plus 1 equals 8 plus 1, and that is equal to 9. Lastly, we have the fifth term, which is n equals 5. So, a sub 5 equals 2 times 5 plus 1, and that is 10 plus 1, which is equal to 11. What about if we will find the 12th term of the said sequence? So in this case, we have n that is equal to 12. We have, therefore, a sub 12 equals 2 times 12 plus 1 equals 24 plus 1, which is equal to 25. We have just determined the terms of a sequence given its general term. This time, we are going to do the reverse. Given the first few terms of a sequence, this time, we are going to determine its general term. Let's have an example. Given the sequence 2, 11, 26, 47, and so on, let us determine its general term. In the first four terms, it can be observed that each is 1 less than thrice the square of n. A sub 1 equals 2, which is 3 times 1 squared minus 1. A sub 2 equals 11, and that is 3 times 2 squared minus 1. A sub 3 equals 26, and that is 3 times 3 squared minus 1. A sub 4 equals 47, and that is 3 times 4 squared minus 1. So, a sub n equals 3 times n squared equals 3n squared minus 1. Therefore, the general term of the sequence 2, 11, 26, 47, and so on can be expressed as a sub n equals 3n squared minus 1. Let's have another example. Find the general term of the sequence whose first 5 terms are 1/2, 3/4, 5/6, 7/8, 9/10, and so on. Observe that the numerators of these fractions are the odd numbers and the denominators are the even numbers. Numerators are as follows: 1, 3, 5, 7, and 9. And the denominators are as follows: 2, 4, 6, 8, and 10. Even numbers are usually written in the form 2n, and odd numbers are usually written in the form 2n minus 1. Remember, an odd number differs from an even number by 1. So, if the numerator is denoted by 2n minus 1 and the denominator by 2n, then a sequence that has these numbers for its first 5 terms is given by a sub n equals 2n minus 1 all over 2n. Let's take another example. Find the general term of the sequence 1, 3, 5, 7, 9, and so on. What do you think is the general term? So what's your answer? If your answer is a sub n equals 2n minus 1, then you are right. Now, let's observe closely the sequence. Again, the terms are 1, 3, 5, 7, 9, and so on. Let's subtract 2 consecutive terms. So we have 3 minus 1 equals 2. Another pair, 5 minus 3 equals 2. Let's have another consecutive pair. 7 minus 5, and again, that is 2. Lastly, 9 minus 7, again, it's equal to 2. So, you notice that the differences that we obtain are the same, which is always equal to 2. So there is a common difference, correct? And if the sequence has a common difference, then we say that that sequence is what we call arithmetic sequence. So what is an arithmetic sequence? An arithmetic sequence is a sequence where every term after the first is obtained by adding a constant called the common difference, denoted by D. Now, let us consider an example. Determine if the sequence is arithmetic or not. If it is, find the common difference in the next three terms. So the sequence is negative 17, negative 10, negative 3, 4, 11, and so on. So, to find out if the sequence is arithmetic, there must be a common difference between any two terms in the sequence. Now, let's find out. Finding for the difference, or D, we have a sub 2 minus a sub 1, which is negative 10 minus negative 17, and that is equal to 7. Next pair, to get the common difference, we have a sub 3 minus a sub 2, and that is negative 3 minus negative 10. Simplifying, we have 7. Next, getting the difference between a sub 4 and a sub 3. So we have 4 minus negative 3. And that is, again, it's 7. Last, difference of a sub 5 minus a sub 4. So we have 11 minus 4. And again, the answer is 7. Therefore, the sequence is arithmetic. Why? Because the sequence has a common difference of 7. The next three terms, therefore, can now be obtained by adding D, which is 7, to the preceding term. So that, for us to get the sixth term, we have a sub 5 plus D, which is 7. So that is 11 plus 7, and that is 18. Continuing to get a sub 7, we have a sub 6, and adding D, 7. So we have 18 plus 7 equals 25. Now let's find the eighth term. So we have a sub 7 plus 7 equals 25 plus 7, and that is 32. Now, it's your turn to identify whether the sequence is arithmetic or not. If it is, find the common difference, which is D, and again, the next three terms. So, first we have the sequence 2, negative 4, 6, negative 8, and 10, and so on. Again, 2, negative 4, 6, negative 8, 10, and so on. And the next sequence is negative 1, 2, 5, 8, 11, and so on. And again, negative 1, 2, 5, 8, 11. Is the first sequence arithmetic or not? If your answer is no, then you are correct. The sequence does not have a common difference. Let's try to look into the solution. Negative 4 minus 2 equals negative 6. Looking at the difference of the next two consecutive terms, we have 6 minus negative 4 equals 10. By that, we can say that there is no common difference. Now what about the second sequence? Is it arithmetic or not? If your answer is arithmetic sequence, then you are right. The sequence has a common difference of, correct, the common difference is 3. Let's look into the solution. So, 2 minus negative 1 equals 3. Let's look into the difference of the next two consecutive terms. 5 minus 2, again, it's 3. Another pair, 8 minus 5 equals 3. And lastly, 11 minus 8 equals 3. Since the sequence is arithmetic, then let us find the next three terms. The next three terms are 14, 17, and 20. Suppose we want to find the 20th, 50th, and the 100th terms of the sequence. How do you find them? We use the formula a sub n equals a sub 1 plus n minus 1 times d, where a sub n is the nth term, a sub 1 is the first term, and d is the common difference. Now, let's have examples. Find the 10th and the 100th terms of the arithmetic sequence for which the first term is 8 and the common difference is 5. So first, let's look into the 10th term of the sequence. Since d equals 5 and a sub 1 equals 8 and n equals 10, then we can easily find the 10th term of the sequence. By the formula, a sub n equals a sub 1 plus n minus 1 times d, and by substituting the given values, we have a sub 10 equals 8 plus 10 minus 1 times 5. Simplifying, we have a sub 10 equals 8 plus 9 times 5, and this is equal to 8 plus 45, and we have the resulting equation as a sub 10 equals 53. Thus, the 10th term of the sequence is 53. Now let's find the 100th term of the sequence. So given a sub 1 equals 8, this time n equals 100 and d equals 5. To find a sub 100, again let's substitute the given conditions in the formula. A sub n equals a sub 1 plus n minus 1 times d. So a sub 100 equals 8 plus 100 minus 1 times 5. Simplifying further, we have 8 plus 99 times 5, and this is equal to 8 plus 495. So, a of 100 equals 503. Therefore, the 100th term is 503. Let's have another example. In the arithmetic sequence, negative 16, negative 9, negative 2, 5, 12, and so on, which term equals 180. So let's look into the given. A sub n equals 180. And what is a sub 1? Is equal to negative 16. And what is d? d equals 7. Now, let's find n. Substitute the given values in the formula. A sub n equals a sub 1 plus n minus 1 times d. So we have 180 equals negative 16 plus n minus 1 times 7. Simplifying, we have 180 equals negative 16 plus 7n minus 7. Simplifying further, we have 180 equals 7n minus 23. Applying the addition property of equality, we have 180 plus 23 equals 7n. Thus, we have 203 equals 7n. And then, multiplying both sides of the equation by 1/7, we have n equals 29. Therefore, 180 is the 29th term of the arithmetic sequence. Before we end, let us summarize what we have learned today. First, a sequence is a function whose domain is either the set whose elements are 1, 2, 3 up to n, where n is a natural number, or the set of positive integers. Second, every element in the sequence is called a term and denoted by a sub 1, a sub 2, a sub 3, a sub 4, and so on. Third, there are two kinds of sequence: the finite sequence and the infinite sequence. Fourth idea, a sequence is said to be finite if its domain is a set of 1, 2, 3, up to n. Fifth idea, a sequence is said to be infinite if its domain is the set of positive integers. Sixth, an arithmetic sequence is a sequence where every term after the first is obtained by adding a constant called the common difference denoted by d. Seventh, to identify if a pattern is an arithmetic sequence, we must examine consecutive terms. If all consecutive terms have a common difference, you can conclude that the sequence is arithmetic. 8. To find the common difference, which is d, simply subtract the first term from the second term, or a sub 2 minus a sub 1, or the second term from the third term, that is a sub 3 minus a sub 2, or the third term from the fourth term, or a sub 4 minus a sub 3. And lastly, to solve for the nth term of an arithmetic sequence, we use the formula a sub n equals a sub 1 plus n minus 1 times d, where a sub n is the nth term, a sub 1 is the first term, n number of terms, and d is the common difference. That is all for today, my dear learners. I hope you learned a lot from today's session. See you on our next episode. Always remember, stay safe and enjoy learning mathematics. Good day, everyone.